The last question in the warm-up is to sketch a picture or a graph to represent the series from n equals 1 to infinity of the function 6 over the square root of n. Now, if we were to write this as a continuous function, or at least a function of a continuous variable, we would be able to take the derivative and find that the derivative of this function is going to be 6 times 1/2, which will be 3, times x to the negative 1/2. And so we have 3 over the square root of x. Rather, that was already negative 1/2. Let's just go back and rewrite the function first in derivative-friendly form. 6 times x to the negative 1/2. Then the derivative here is going to be negative 3 multiplied by x to the exponent negative 3/2. And that's going to give us negative 3 over x square root x. And if we take values of x to be greater than 1, greater than or equal to 1, we know that the denominator will always be positive, and therefore the derivative will always be negative. This tells us then that the original function f of x will be decreasing on the domain of x greater than or equal to 1, which means that the sequence terms of 6 over square root of n for the integer values n equals 1, 2, 3, etc. will also be decreasing. Furthermore, we can see just by inspecting the values on the same set of x values that the function is going to be positive. So we have that f of x is greater than 0 for x greater than or equal to 1. So we can sketch this graph with use of technology, or maybe we know what it looks like already. But when we do come up with a graph, it's going to be a positive decreasing function. Something like this. Now this is the graph of f of x because we are not just restricting ourselves to using x equals 1, 2, 3, etc., but we are using all of the real values of x in between the integer values. So I've come up with a couple of integer values here so that we can represent the series. And we know that this is going to be 6 over the square root of 1 plus 6 over the square root of 2 plus 6 over the square root of 3, etc. And those y values are going to be, I'm going to make that series in red. So if I change the color here, I can plot those points now in red associated at the y coordinates. And of course there's going to be more of them, but this is enough to get the idea. And what's going on here is that we have each of these numbers can be thought of as multiplied by 1. And so now this is becoming very familiar to look like the area of a rectangle. And so we have an infinite number of rectangles that are associated with this continuous function. And we want the height of each rectangle to be given by the red number and the width to be given by 1. And that's convenient because each of these widths for consecutive integer values already is 1. So we can make the first term of the series look like a rectangle of area given by length times width of 6 over root 1 times 1. And then we can do another one using the left end point of this series to represent the infinite sum, the infinite series. So the question then says to compare the value of the sum with the integral. Now this is an improper integral because even though x is equal to 0, or when x equals 0, that produces a vertical asymptote, we are not including x equal to 0 in the bounds of the integral. So we can work this out as an improper integral because we have an infinite width. So when we do that, let's just quickly shade under the graph. We know that the improper integral is going to represent the accumulation of this infinitely long curve. And the question of convergence is really saying, does the accumulation exist? Is it defined? Is it real, single, and finite? So to do that, if we want to work out the improper integral from 1 to infinity of 6x to the negative 1/2 dx, we are going to set it up as a limit first. And we work from the inside out. So we work on the antiderivative first, and then evaluate according to the fundamental theorem of calculus, and lastly we will work out the limit. So we have a simple antiderivative here. We add 1 to the exponent, and then we divide by the new exponent. Now dividing by 1/2 is the same as multiplying by 2. And I'm just going to rewrite this function in integral or evaluation friendly form. So we're going to get 12 times the limit as t approaches infinity of the square root of t minus 1. Now we're no longer really thinking about accumulation. We were thinking about accumulation up until here. But once we no longer have an integral, we are now thinking about a new function, and we're really looking at, for the limit as t approaches infinity, this implies the right end behavior of a different function. And so this different function is no longer the 6 over square root of stuff function, but it's the 12 times the square root of t minus 1 function. And the only piece that really matters here is the square root of t looking like this increasing function. And so as t approaches infinity, the square root of t also approaches infinity, and we have that this limit is equal to infinity, therefore does not exist. And what that means on our graph, the accumulation on the original function, is that we do not have a finite accumulation in yellow. And it looks like the red accumulation, which is the one that represents the series, is bigger than that. And so if we have a sum or an accumulation or a value that is bigger than infinity, it suggests that that bigger value does not exist, is not a real single or finite, in this case, finite value. And so it looks like that series diverges. So that concludes the warm-up video. Stay tuned for more on series.